group in attendance, as I'm pretty sure is like kind of a low-key size lunch tradition. So I'm going to nominally be talking about the GNSS acoustic measurements that we are collecting and have collected in the offshore Cascadia and Alaska subduction zones. This is work that is highly collaborative. I'm definitely not the only person working on this project. There are a number of people at Scripps, UW, USGS, people who operate the research vessels, deploying the instruments. It really is a very large effort across multiple institutions to collect these data. So even though like what I'm going to show is like kind of like sparse in the relative things, it's a large amount of labor in order to get even one measurements, because they really are high value. And I hope that this talk convinces you that they are high value measurements that are worth expending so much resources to collect. So I wanted to open up by actually talking about the GNSS acoustic technique itself, just so that we're all on the same page. Please bear with me. I am a methods guy, so I like digging into the methods, but I guarantee there will be no math whatsoever in this talk. So like you can feel comfortable with that. The basic gist is, yes?
You use the 3 dots, I think you get rid of it.
Oh,
I don't know how to.
so fun stuff is that I can't see it from the laptop screen. Thank you for telling me that it's
You know
there.
what you're saying? I give them tutorial, but this is
Under more high footing.
Oh no, I just tried clicking on it, but it clicked on the slide.
I'm tired of it. We'll do it.
Oh boy. So to continue, move on. So the GNSS acoustic, the driving motivator for this is that we want to be able to collect geodetic measurements in an offshore environment. And the standard terrestrial geodetic techniques, GNSS, INSAR, these are very well established, very powerful tools. And you can apply them to a marine setting, and they work very well. The electromagnetic radiation, the radar from the satellites gives you about that much penetration in seawater, which is marginally shallower than most of the ocean, but it's a start. So the way we address this is we adapt specialized tools in order to try and replicate, in this case, GNSS. The way we do it is by deploying a 2-tiered system. We have instruments on the seafloor and an instrument platform on the sea surface that are communicating with each other acoustically, leaning on the fact that sound travels very, very well through water, whereas electromagnetic radiation, not so much. And then since the platform is on the sea surface, it can use standard GNSS just fine, because the only thing between it and the satellites is the atmosphere. So the first principle really of how do you position a thing on the seafloor, if you're communicating acoustically with the transponder on the seafloor, you're on a sea surface platform, there's very standard seismic observation that if you have like some travel time, in this case, and it's traveling a wave along some ray path, if you know the slowness of the media, you can predict what that travel time is going to be. And this is fairly straightforward. Kind of the next step in what makes GNSS acoustic work is the idea that if you take a difference between 2 ray paths to 2 different points on the seafloor, one point that kind of an a priori transponder position, and some other point you don't know, in this case, the real position of the transponder, you can do that same thing where you take the 2 ray paths, you multiply by the slowness, and instead what you'll get is what we call an acoustic travel time residual. This is basically you go out, you measure your travel time, you have a real number, then you use all the information that you have about the ocean in order to try and predict what that travel time is. And the difference between that prediction and what you actually measured gives you information about how far away the transponder that you are trying to locate is from where you initially thought it was. And so and the model for the ocean can be pretty simple. Like the basic gist is that you can just take a straight ray path through the ocean and multiply it by the harmonic mean sound velocity, and that's pretty good, if naive. So this is just kind of like a step-by-step of how we actually set up our position inversion, and it's more or less what I just described, where you model what you think the ocean looks like using the most like foolish and naive assumptions, and then you blaze forward, and it ends up working surprisingly well. So this is an example of some of the data that we collect and process. So each of these three plots is a time series of acoustic travel time residuals for each of the three transponders in a GNSS acoustic array. This is what I've described. We measured the travel times, we difference them with a model prediction of what they are, and this is what it looks like. And we can see, shockingly enough, the ocean is not static. So maybe our foolish, naive assumptions of how it behaves were a little foolish and naive, because there's a pretty clear tidal signal through all of these GNSS acoustic residuals. But I mean, we could model the ocean better and maybe try to account for this, or we could do something a little less difficult. Because we know what the ray paths are to the transponders, because we calculated them in making our model, we can decompose these residuals into east, north, and up components. Because not only the residuals themselves is like some fraction of a ray path that's pointing in that direction. So if we decompose all of these time series into their individual components and then average them all together, get something that looks like this. So these are the same time series. This is the east, north, and vertical. And because we're looking at an average of these east, north, and vertical components of the ray path, we can really consider this to be the bulk position of the entire GNSS acoustic array, or rather the nominal position of the center of the GNSS acoustic array. And we see something quite magical here, whereas before there was all this tidal signal in the residuals, the average east-north component are pretty precise. They've been reduced to fairly constant within about a 2 centimeter band of the average position. The vertical is not looking so good. All the oceanographic signals mapped into that, so maybe we'll just throw away this component and lean on these, which are pretty precise. I'll also apologize for using the M word, but yeah, I think it's a pretty neat observation here. So this really is the crux of GNSS acoustic, the idea that one transponder you can't position particularly well because, well, the ocean is this complex beast of a thing that we can't really describe perfectly in real time. But if you deploy transponders in array and average their positions from the center of the array center looks pretty stable as long as the ocean is a horizontally layered medium, approximately, which oftentimes it is. Then even if the sound velocity is varying beneath the surface platform, the transponders will either all appear to move out or move in, but they'll be moving in tandem with one another, and the center appears an invariant point. We can use that.
Question?
Yes.
What does the acoustic signal look like? Is it a single frequency? Is it a chirp?
It's a chirp.
It's a chirp.
Yeah. I saw another hand go up. No? Okay. So the actual instruments that we're using to run these experiments, I've talked about transponders, I've talked about surface platforms. The surface platform is a liquid robotics model SV3 wave glider shown here in this picture. This thing, it's solar powered, or rather I should say it's a wave glider. So it passively harvests wave energy in order to propel itself forward, and then it has a solar powered scientific payload. We can put this thing off and it can go out and just sail around for about 2 months. It can go out for longer, but 2 months is kind of the amount of time I'm comfortable with it out.
Can I,
Yes.
you had data gas earlier in your slide, you
Yes.
said recharging.
Okay, so those data were collected by an older wave glider, not pictured here, that we used to use. That time series was from 2019. And the older wave glider only had enough battery power in order to run GNSS acoustic payload for about a day and a half before needing to shut everything down and recharge the solar powers. So that's why those data gaps were there. The SV3 has much more battery capacity, so that's less of a thing now, although if the sea state gets really rough and choppy, right now we just had a wave glider down in New Zealand, like weather the cyclone, and we're now like starting to try and restart the payload. Just ocean things. Yes?
So on the previous slide, you said, well, you can really get rid of a lot of the tidal signal, but that the variability is still like several centimeters.
Yeah.
And to measure seafloor deformation, that's still pretty big.
Right. So the other thing that I forgot to mention, but which I should clarify, is that with a time series like this was one occupation over the course of many days at a single site. We have all these individual positions, but for a survey, what we're going to do is, in order to try and further reduce this variability, we're going to average this entire time series into a single position for the entire survey, and that will help beat down more of the noise. So the other sort of trick is that not only do we average in space, we average in time. And when you average just over everything, then like the final position you get is pretty good. So back to the instruments, wave gliders are wave gliders. Transponders are acoustic transponders. This thing just, you toss it off the side of a vessel, it sits on the seafloor, and when it hears an acoustic pulse from this guy, it replies back with a pulse in kind. One neat thing about the transponders, so they're deployed on these concrete benchmarks, which is really nice because the transponders have a finite battery life associated with them. But with the concrete benchmarks, you can recover a transponder after or once its battery is about to run out, and then you can go back to the site later and set a new transponder with a fresh battery onto the benchmark. And because of the benchmark design, it locks into place to within like a few millimeters or so, and you can just continue your time series past the lifetime of a single instrument, which is pretty cool. This is a routine operation that we've done multiple times. So that's the background. Thank you for entertaining me with that. Now let's talk about the stuff that you're actually interested in. So Cascadia, I hope that I wouldn't have to spend too much time introducing the region, since the audience in the room is acquainted with it. But the basic gist is that on-land geodetic stations don't really have the resolution in order to image what the deformation offshore is like. And so in order to address this, we really need seafloor geodetic instruments, and it's particularly salient here in Cascadia because, well, we have the threat of a large megathrust earthquake offshore, and like the resulting tsunami would be like muy bad. So that's the motivator for deploying GNSS acoustic instruments in the region. The array that we've been surveying for the course of the past many years is shown in this slide. So there are really 5 well-established GNSS acoustic sites in Cascadia. This westernmost site was deployed on the Juan de Fuca Plate in the mid-90s by Dave Chadwell and others, and has something like a 20-year-long time series constraining its velocity. That's why its air ellipse is very, very small. This red vector is the Juan de Fuca plate motion as predicted by the Nouvelle 1A plate model, and it agrees pretty well with our direct observation. So we take this measurement as ground truth for the plate, for the subducting plate rate. Then these other 4 sites are on the trench. They are on the North American plate. They're deployed in GH1 and in P1 in 2016, in CL1 and in CB1 in 2018. This was a joint effort by Dave Chadwell and David Schmidt. There are too many days. All the velocities, of course, that I'm going to show are in the reference frame of the North American plate. So what that means is that in general, big velocities mean it's traveling with the subducting slab. Small velocities mean that it is just resting on the plate, as you would expect. And we've tried to survey these sites once a year since they were first put down, but you can't always get out there depending on other factors like global pandemics and such. As for how the velocities themselves are calculated, we get, as I mentioned before with Joan's question, we get essentially 1 position a year per survey. And then we just fit a line through them as you get a time series. This is like the highly technical work that getting a PhD prepares you for. So something to note, the different error bars in the velocities really does boil down to the fact that like some of these time series had very few points in them. And so the more data we collect, the better we can constrain the velocities of the sites. What I'm showing you here is like our current best knowledge of what's going on in the region, but our information is only going to improve as we continue collecting data at these sites in the future. So if we were to compare the seafloor geodetic measurements to the land station measurements, there are a couple things that are worth pointing out. One is that the land stations are very well constrained, whereas the seafloor sites are rather less well constrained. Makes sense considering we have like 3 to 5 measurements for these and like tens of thousands for these. So maybe one day, decades in the future, we'll be able to match that. But the other important thing to really point out is that the velocities on land are much, much smaller than the velocities on offshore. And gradient has some pretty interesting implications for the sites, because really the surface level interpretation is that the seafloor sites, even though they are resting on the North American plate, they really are moving with the subducting slab. Whereas once you get onshore, the sites are mostly moving with the North American plate. They're stable or more stable. So a naive conclusion that we might draw from this is that because the seafloor sites are moving with the subducting slab, that there must be a high degree of locking, or if not full locking, right beneath the seafloor geodetic sites, which would be the shallow subduction zone. So we've done like a few modeling studies in order to try and verify this, and that's kind of what we see. This is for one of the sites. It's offshore Newport, Oregon, and the basic gist here is that in order to fit this gradient, as I described, you need like a narrow band of locking or near lock, full locking near the shallow trench. And curiously enough, for this particular model, like kind of the boundary between the lock zone and the transition zone is like right at the slope break, or the shelf break, which is cute, but I'm not sure if it has any geophysical significance yet.
There's a paper from 2 years ago, Luca Malatesta, and he wrote that global looking at down dip edge of the seismogenic zone based on different definitions didn't match coastlines as well as people had thought before, but did match the outer edge of the continental shelf
Oh, really?
globally. So it might be an interesting thing to compare it to.
Yeah.
Which makes sense. I mean, the continental shelf is the low stand. It is the continental edge in a way, because that sea level goes up and down, but that's why there's a shelf.
Yeah. I would also be remiss, that's kind of the extent of like our interpretations for the Cascadia subduction zones as of now. We could spend quite a lot of time just looking at the cute little map that I put together with all the vectors on it.
I have one more question.
Sure.
The northern site off Washington, you guys have said it hasn't had many occupations, so it's harder to analyze whether that vector difference is different. Why does it have a smaller error ellipse than the other ones?
It has a smaller error ellipse because the three measurements that we've collected happen to have low scatter from a straight line. So, I mean, that's the reason why. Yeah, I mean, we can discuss whether or not like you trust like formal uncertainties or not, but
Fewer observations, but they happen to be
fewer observations. They happen to fit a line pretty darn well. So like, yeah, you get a small error bar out. That's a site that we would like to reoccupy as soon as we can. Like when that'll be is still up in the air, but yeah, we want to get a better constraint on that velocity. And speaking of getting better constraints, I would be remiss not to mention the seafloor geodesy community experiment. This is actually underway, and the goal in Cascadia is to deploy 6 new seafloor geodetic sites, GNSS acoustic sites, that are represented by these red dots here. These southern 3 sites we actually deployed during a research cruise last July. So they're in the water. There is also a set of USGS deployed GNSS acoustic sites off the Gordo plates as of last May. So they're nearly a year old. And there is also a recently established array of 7 Canadian GNSS acoustic sites north of the border off of British Columbia. So within the next few years, we hope to have a pretty robust array offshore Cascadia to really pin down some of the holes in our previous observations, particularly up in the north, where things are a little more sketchy. So that's what I have to say about Cascadia.
Can I ask?
Sure.
So the linear trends you showed for the correlations, it looks like every 6 months you could still better constrain the linear regression. So what is the limitation for the annual? The annual cruise is just modeling, or is it? Because every 6 months
there are a couple of things that are going on. One thing that needs to be appreciated when we're talking about when we can go out and collect data at the sites is that Cascadia offshore is pretty rough during the winter months. It doesn't have a lot of sunlight to power a solar payload. So nominally our field season starts up kind of in around May and runs through October at the latest. Right. Right. And then during the winter months, you'd rather not put the instrument out there, the wavelet out there to collect data. So nominally the mode that we've been working in is try and get a survey in during the summer months when the seas are calmer and we have more sunlight available. Yes.
Maybe this is a dumb question, but disregarding your interpretation that near the deformation front, it's gotta be highly coupled because it's moving with the subducting plate. Is that?
Yes.
But
Yes.
you have, your monument is sitting on a big pile of sediment.
Right.
Is the coupling that's going on at the interface, is it really behaving like a rigid block that's glued to the interface? Or does this, it seemed to me that the sediment would be kind of a very sloppy, I don't know, maybe that's a dumb.
I don't really, I mean,
So the way I would look at it is the three southern sites that we have, John, if you go back to the map,
yeah,
they're all pointed generally parallel to each other. So if it was really just a giant sand pile that was collapsing, then you would have vectors going in all different directions.
And it would collapse the other direction.
And it would, yes,
Yeah.
collapse. So
Those sediments are rock, man. Plate interface, this is my ADU talk, right? At the plate interface, all the way to the deformation front, seismic velocity in sediments is 4,000 to 5,000 meters per second. It's rock. It's, people love to think of this as a sand pile. It's just wrong. Sorry, it's one of my so. It's, yeah, soft rock, but okay, it's not the salt.
But John, also just to comment on your question, there is the question of how, what the stability of the benchmark is, because it is just resting in sediment in the basin.
Yeah.
And so one of our concerns is how stable is that sediment benchmark for long periods of time? Will it continue to settle? Will it start to tilt? We don't know the answer to that.
When they talk about the accretionary prism sediments, it's really not.
Sedimentary rock, think sandstone. I mean, not at the surface. I mean, David's absolutely right. There could be at the surface, you could have an unstable site because of downslope processes or something. But in terms of being fixed to the bottom versus fault slip, to me, these measurements are showing you what that whole multi-kilometer thick pile is doing.
Okay.
Yeah, and the fact that it's moving in the same vector generally, with that northern site being slightly different azimuth, it's just more evidence that that's true.
I have another question, which relates to my CMS, but these are very angled to the trench axis. So how is the slip partitioning accommodated in kinematic models? Is it, how does that?
Yeah, so when we do the modeling, all of these vectors get rotated relative to the core. And so there's a correction made to all the velocities. And so when you do that correction, then it's just slightly oblique. It's mostly downhill. When you talk about Juan de Fuca relative to the 4R. Because these are relative to North America, this reference frame that John is showing right now.
Okay, got it, yeah. Thank you.
Yeah.
About your geometry of the station. I'm curious, I know you want to understand locking of the trench, but would there be, like, with all the time and nothing, would there be any value to moving that like, to the coast, or is that just you have good enough station coverage at the coast?
So the short answer is yes. Like there's absolutely value in moving up on the shelf. There are a couple of reasons why we haven't done so as of yet and why we don't have any plans to do so in the immediate future. One is that there have been a number of studies that show that like kind of when you have a very sparsely covered system, subduction zone like this, you get the most amount of new information by deploying directly at the trench. And another issue is that up on the shelf is actually pretty dangerous for instruments like this because you have a lot of trawling fishermen. And so we have a lot of paranoia that like we put a site up there, might get like a year, maybe 2 years of good data from it. But then like it only has to happen once for someone to like just sail on through, pick up one of the transponders in the array. And then like the measurements are all worthless. There is an engineering inquiry that our colleagues at Scripps are pursuing, to my understanding, in order to try and develop a trawl-resistant concrete benchmark to house these acoustic transponders. That's very much still a work in progress, and we'll just have to see if that inquiry bears fruit. So, yeah.
Does the OI cable have any site?
No. We don't have a site cabled with OOI. Although it's worth mentioning that the Canadians do have one, maybe 2 sites that are cabled. The issue is that the cable would be able to provide power to a transponder, which would be really nice because you could keep the instrumentation down on the seafloor for longer, but that wouldn't necessarily enable continuous data measurements because you'd still have to deploy a surface platform to the region. There have been studies that have been done with anchored buoys as a surface platform, but it's not necessarily a solution to the problem because a buoy has less control over where it can position itself on the sea surface. So you're not always observing the array from where you would like to observe the array. You're kind of at the whims of the surface currents. Are there any other questions? Okay, I'll talk briefly about Alaska then, because we do have some very interesting observations in Alaska. The array up there was established in 2018. It consists of these 3 sites, SEM1, IBB1, and SPT1. They were deployed to nominally try and measure the change in shallow subduction zone locking across the Shumagon Gap, which is this region of the Alaska subduction zone that hasn't seen a major, i.e. like Bag 8 or larger earthquake in the last century or so. But then this interesting thing happened in 2020 and 2021. We had this sequence of earthquakes that happened like right there. The first is the Simeonov earthquake. This is the mag 7.8. Sand Point is mag 7.6, and then 2021 the Chignik earthquake is mag 8.2. So those earthquakes happened, and the primary stated goal of this array very quickly morphed into let's measure the seafloor offset and afterslip from these earthquakes. It just happened in the region. This is the slip of rupture area of the Simeonov, this is rupture area of Chignik. And so really each of these 3 sites, we were able to observe seafloor offset from the closest earthquake. So the first one, Simeonov, we were able to survey it in the months following the earthquake. This was a large rapid response effort collaboration of like many people whom I mentioned at the start of the talk. And we were able to measure about 16-ish or so centimeters of offset after the earthquake. This is a co-seismic offset that we've estimated by trying to parse out what fraction of the total offset is post-seismic and what fraction is co-seismic. I prefer not to bore you with the details. The most interesting thing about this is that the offset vectors on the land stations are quite a bit larger than at the seafloor station. This is because the rupture area was primarily pretty deep. Some kinematic rupture models, the one on the right was published by our very own Brendan Crowell soon after the earthquake. And this was with all of the on-land teleseismic and GNSS data collected by the Earth immediately following the earthquake. The model on the left is our own. It's the exact same, except we've added the seafloor offset. And the interesting thing to note is that a lot of this slip in the previous model, like this is like kind of background noise and such. And there's a fair bit less of it, a little less of it in the model with the seafloor offset, especially in the immediate surrounding region of the seafloor site. Otherwise, not much of the rupture has changed because this was primarily a deep rupture. The seafloor side is above the shallow part of the plate interface where we don't expect a lot of slip to have happened. But it's still a very valuable constraint to confirm that, yes, indeed, this was a deep rupture and did not have phantom slip up dip that we couldn't measure at the land stations. A fun thing that we can do is use this as an opportunity to test how sensitive the seafloor site is to its immediate surrounding region. And so the way I like to do this, since I come from a physics background, I look at something like the rupture and I immediately say like, oh yes, this looks like an exceptionally well-fed farm animal. So I'm going to model the rupture as a Gaussian, same like peak slip as the rupture model predicts. It actually has less moment because the curious thing about Gaussians is that once you go a few standard deviations away from the center, it essentially goes to zero. So that background slip that's in the rupture model doesn't exist in this little toy thing that I put together. And so as a result, it has less moment. But basically, I'm going to take this Gaussian rupture approximation roughly of the Semyonov earthquake. I'm going to slowly shift it towards the seafloor site just to predict how much offset we measure at it. And that's what's shown in this graph on the left. And really a key note are these two thresholds here. This bottom threshold is at a centimeter. That's like roughly what we like to nominally say the sensitivity of a GNSS acoustic position is. And then this upper threshold is the offset that we actually observed from the earthquake. And so the idea is these thresholds are plotted as the bullseyes in map view. So the idea is that if slip from the earthquake intruded upon this outer threshold, then we would be able to measure it with the seafloor site, or you would expect to measure it. If it moved past this inner threshold, then we would expect to measure more slip than we actually saw after the earthquake. And so this gives us an idea that like kind of within 100 kilometers or so of the site, like we would expect to have a response in the GNSS acoustic measurement from this particular kind of earthquake rupture, which is a neat little conclusion, in my opinion. The Chignik earthquake is an 8.2, very big. And it's basically the opposite story, where this rupture actually came up pretty close to the seafloor site. And so We measured a meter and 40 centimeters of offset. Compared to where the site was before the earthquake and like in the months after the earthquake. So this is much, much larger than was predicted by just the immediate teleseismic models following the earthquake. So this is an earthquake that must have been shallower than initially predicted, and pretty significantly so. The details, I won't go too far into them, but they're in a paper by Ben Brooks that was recently accepted to Science Advances, and with luck will be published shortly. So I encourage you to search that out if you're really curious about it.
What do we know about shadow afterslip? Like this may include shadow afterslip, but I actually have don't quite understand whether or not the shadow afterslip can be pulled out. Like I'm used to seeing a patch of slip and then some afterslip when there is
Right.
cavity or something in the slip zone. But how much the shadow subduction zone does not rupture seismically often, then
Yeah.
afterslip compensate for that or catch up.
So short answer is I don't know. Slightly longer answer is that we've been back to this site one more time in 2022, and in the year since we've measured like another 20-30 centimeters of offset at the site. So there is definitely a post-seismic after-slip response that's going on that is still like not resolved. We'll probably be measuring that signal for the next few years.
Cool. But here where you say, and this might be in the paper, but 1.4 meters co-seismic and a few months of offset, is that two separate measurements that were taken at two different times?
What that is boiling down to is that this site was occupied in 2018, 2019, and 2021 in the months after the earthquake. The earthquake happened in July, and I think the earliest they were able to get the wave glider out there was in like September to collect data over the course of a week or two. And so the idea is that naive analysis is like, okay, we have like a rough velocity prior to the earthquake. You project that out to when the earthquake happened in order to get an idea of where the site was positioned when the rupture happened. And then you take a difference with what we measured like 2 months or so after the earthquake, and they simply just didn't do the analysis to try and decompose that offset into co-seismic and post-seismic parts. So instead, this is an offset of 1.4 meters co-seismic plus a few months post-seismic, and what those components are, we don't really know.
But that's assuming the same background separate before and after the earthquake.
Yeah.
Could you have a few data points and then use some model of an exponential decay of afterslip to back project what you think those early months might be? I mean, there's no way to test it, I guess. Like if you got 20 centimeters over some time span that's relatively long time after the earthquake, then there should be some function for what the early times were.
Yeah, I mean, this sounds like the type of project that, yeah, this sounds like the type of project to me that like someone might write their thesis about. So
There used to be, and I think still is an unresolved debate about how much viscoelastic post-earthquake rupture deformation takes place versus fault slip. Because they both have this kind of exponential decay possibly. And I'm just wondering if this, because this is so shallow, you don't really, I think the viscoelastic response would be really muted from the site. You might be able to address that question a little bit. I don't know.
yeah, perhaps.
You call it after slip, but someone might say, oh, it's just that it's viscoelastic deformation.
I call it after slip because I'm towing the line in the paper. So I'll maybe wrap up the talk by speaking a little bit about the last of the earthquakes, the Sandpoint earthquake. This is the mean one. So in the plot to your left, I've plotted up the coseismic offset that we measured at SPT1 following the earthquake. This earthquake actually happened literally a day and a half after we recovered the wave glider from our first position of this site. We then were able to twist the arms of the crew of Sikuliak to redeploy the wave glider as they were passing by again a month later. So really that vector is coseismic, literally coseismic, plus a month of post-seismic. For as far as I'm concerned, it is the coseismic, although you could rightly tell me that I'm wrong. There is some post-seismic signal in there. Really the story with this earthquake is that from all the teleseismic, it appears to be a strike slip earthquake. That's what the beach ball I plotted is. And really our offset I measured pointing towards the northeast, that agrees reasonably well with the predicted strike slip offset at the seafloor site. But the reason why not a lot has been published on this earthquake yet is because there's a lot of circumstantial evidence that a simple strike slip earthquake doesn't fit all the observations. In particular, this earthquake, despite being the smallest, produced the biggest tsunami of the entire sequence. It is the strike slip. Where's the vertical? So there's that. The tide gauges data really is like sort of the smoking gun that like there's something more interesting going on here. Multiple folks have tried to model some combination of like strike slip and megathrust during this earthquake, but it's all kind of inconclusive. All the slip really just maps onto the strike slip component followed, nothing maps onto megathrust because the teleseismics really fits the strike slip well and doesn't have an apparent megathrust component to it. Yeah.
There were islands over there that are pretty forwards. It's interesting because the rest of the northeastern part does not have any topography height.
Yeah.
And so this one seems to have an extended topography height because the islands are going toward the trench. So like upward motions could be present because these islands are above the water.
Yeah. But there's one thing that I want to bring up before I end the talk, and that is this. So we reoccupied this site last summer, and this is plotted the offsets between November 2020 and I think August 2022. So 21 months since coseismic rupture. So this is post-seismic, and I think this is just a really good visual explanation for why the seafloor geodetic measurements are so valuable. If we look at everything in total, orange vector is coseismic, purple vector is what we've measured post-seismic, and green vector is the total offset that we've observed at the site. And the remarkable thing is that the post-seismic response appears to be primarily along the megathrust, or what one would expect from a megathrust response. And now there are some caveats here. There is probably also signal from Semyonov and Chignik post-seismic that's bound up in this vector as well. So with so few data points, it's like maybe a little perilous to make a really like strong conclusion from it. But I think this is solid evidence that this event has a lot more complexity that hasn't yet been observed from solely the on-land stations, and that really there's an interesting story that's to be told here from the offshore measurements. Also, I think it's really cute that even though the initial coseismic offset of the site was to the north, that the site is now sitting more southern than where we initially measured it. So to wrap up, there will also be a community seafloor geodetic experiment going on in Alaska, 6 new sites, 3 to the east, 3 to the west of this currently existing array. All the transponders at the existing sites have been recovered at this point, and our hope, current plan is to deploy everything in 2024 so that we can continue measuring the response to these earthquakes, among other things. So a lot of exciting work to be had. I'll open the floor to questions, although y'all have asked a lot of really good ones already. So that's what I've got.
What's the strain accumulation then on Cascadia? Because you have one on the oceanic plate, and then you have a couple on the continental shelf. So you could get